this module, you will learn about the first law of thermodynamics and specific heat capacity. You have already learnt that there are two different ways to transfer energy to a system. One is by heating the system, and the other is by doing some work on the system. The internal energy of the system may change during this exchange of energy with the surroundings. The relationship between the three important physical quantities, heat, internal energy, and work, is expressed by the first law of thermodynamics. The first law of thermodynamics states that the change in the internal energy of a system is equal to the heat absorbed by the system minus the work done by it on the surroundings. Consider a system of a given mass of gas in a container with a movable piston. When the gas is heated, let the heat energy absorbed by the gas be delta Q, and the work done by the gas while expanding be delta W. During this entire process, if the change in the internal energy of the gas is delta U, then, according to the first law of thermodynamics, delta U is equal to delta Q minus delta W, or delta Q is equal to delta U plus delta W. Note that the first law of thermodynamics is an expression of the general principle of conservation of energy. It is important to note that both delta Q and delta W can be positive or negative. If heat is absorbed by the system, then delta Q is positive, and if heat is emitted by the system, then delta Q is negative. Similarly, if work is done by the system, then delta W is positive, and if work is done on the system, then delta W is negative. What is the work done by the system? Let us derive an expression for the work done by considering gas in a container with a movable airtight piston of cross-sectional area A as a system. Let the pressure of the gas be P. Then, the force exerted by the gas on the piston F is equal to PA. If we assume that the force has pushed the piston through a small distance delta x, then the work done by the gas is denoted by delta W is equal to F into delta x, which is equal to PA into delta x or P into A delta x. But A delta x is the small change in the volume of the gas that can be denoted as delta V. Hence, the work done by the gas is denoted by delta W is equal to P into delta V. Let this be equation 1. In terms of differential calculus, equation 1 can be written as dW is equal to P dV. Let this be equation 2. Now, If we consider the expansion of the gas from its initial volume of V1 to a final volume of V2, then the total work done by the gas can be written as W is equal to integral dW between the limits V1 and V2, which is equal to integral PdV between the limits V1 and V2. Let this be equation 3. Though we have taken a gas in a regular shaped container to derive equation 3, this equation for work done by a thermodynamic system is applicable to solids and liquids as well. We can also apply this equation in phase changes. If a thermodynamic process is represented by a pressure P versus volume V graph, then the work done by the system can be graphically found. If during a process the volume of the system changes from V1 to V2, then the work done by the system is the area bound by the PV curve and the V-axis for the given range of change in the volume of the system. Let us apply the law to solve a problem. If 1 kilogram of ice at 0 degrees Celsius melts to water at 0 degrees Celsius at normal atmospheric pressure, what is the change in its internal energy, given that the density of ice and water are 920 kilograms per cubic meter and 1000 kilograms per cubic meter respectively, and the latent heat of fusion for water is 335,080 joules per kilogram. Given mass of the ice m is equal to 1 kg. Density of the ice d I is equal to 920 kg per meter cube. Density of the water dW is equal to 1000 kg per meter cube. Latent heat of fusion LF is equal to 335,080 joules per kilogram. On absorbing heat, the ice melts to water. If the heat absorbed by the ice is delta Q, then delta Q is equal to M into LF, which is equal to 335,080 joules. Let this be equation 1. If the volume of ice and water are represented by VI and VW, then VI is equal to M by DI, which is equal to 1 by 920, which is equal to 1.08 into 10 power minus 3 meter cube. Similarly, VW is equal to M by dW, which is equal to 10 power minus 3 meter cube. Therefore, the change in the volume delta V is equal to VW minus VI, which is equal to minus 0.08 into 10 power minus 3 meter cube. Let this be equation 2. As the melting of ice has taken place at atmospheric pressure P equal to 1.013 into 10 power 5 Pascal, the work done by the system in the process delta W is equal to P delta V, which On substituting the values and simplifying gives minus 8.104 joules. Let this be equation 3. Now we can apply the first law of thermodynamics to find the change in the internal energy of the ice. As per the first law of thermodynamics, delta U is equal to delta Q minus delta W. Substituting the values of delta Q and delta W from equations 1 and 3 and simplifying, we have the change in internal energy delta U is equal to 335,088.1 joules. Earlier, you studied that gases have two types of molar specific heat capacities. One is Cp, the molar specific heat capacity at constant pressure, and the other Cv, the molar specific heat capacity at constant volume. Now let us use the first law of thermodynamics to derive the relationship between Cp and Cv for an ideal gas. Consider a sample of mu moles of an ideal gas in a container with an airtight movable piston. On heating, the gas expands at constant pressure. Let the heat absorbed by the gas be delta Qp, where the subscript P indicates that the heat absorbed is at constant pressure, and the change in temperature is delta T. Then delta Qp is equal to Cp into mu into delta T, or delta Qp by delta T is equal to mu into Cp. Let this be equation 1. For a change in temperature of delta T, if the change in the internal energy of the gas is delta U, then, as per the first law of thermodynamics, we have delta Qp is equal to delta U plus P delta V, or delta Qp by delta T is equal to delta U by delta T plus P into delta V by delta T. Let this be equation 2. But we know that for an ideal gas, PV is equal to mu RT. If we apply this law to the above process, we have P delta V equal to mu into R into delta T, or P into delta V by delta T is equal to mu into R. Let this be equation 3. On substituting the values from equations 1 and 3 in equation 2, we have mu Cp is equal to delta U by delta T plus mu R. Let this be equation 4. Now, as a second case, let the same gas be heated at a constant volume. If the heat absorbed by the gas is delta Qv, where the suffix V indicates that the heat is absorbed at a constant volume, and the temperature change is delta T, then delta Qv is equal to Cv into mu into delta T, or delta Qv by delta T is equal to mu into Cv. Let this be equation 5. But at constant volume, the work done by the gas delta W is equal to 0. According to the first law of thermodynamics, delta Q is equal to delta U plus delta W. As delta W is 0, we have delta QV is equal to delta U. Let this be equation 6. From equations 5 and 6, we get delta U by delta T is equal to mu into CV. Let this be equation 7. Note that in both processes, we have taken the change in the internal energy of the gas as delta U. This is because in both cases, the change in the temperature of the gas is delta T, and the change in the internal energy depends only on the change in the temperature of the gas. From equations 4 and 7, we have mu Cp is equal to mu Cv plus mu R, or Cp minus Cv is equal to R. This is the relationship between the two molar specific heat capacities of an ideal gas. You have now reached the end of this module. In this module, you learned that there are two different ways to transfer energy to a system: heating and doing work. The relationship between the three important physical quantities, heat, internal energy, and work, is expressed by the first law of thermodynamics. The first law of thermodynamics states that the change in the internal energy of a system is equal to the heat absorbed by the system minus the work done by it on the surroundings. First law of thermodynamics: delta U is equal to delta Q minus delta W, or delta Q is equal to delta U plus delta W. First law of thermodynamics is an expression of the general principle of conservation of energy. Delta Q is positive if heat is absorbed by the system, and negative if heat is given out by the system. Delta W is positive if work is done by the system, and negative if work is done on the system. Work done by a system, delta W, is equal to P delta V. If a thermodynamic process is represented by a PV graph, then the work done by the system is the area bound by the PV curve and the V-axis for the range of change in the volume of the system. Cp minus Cv is equal to R.